Okay, let's go ahead and start with this next problem. This one is going to be a lot more work than the last two. And as you can see here, I've already kind of highlighted some of the important stuff, and I've already kind of drawn out the geometry because I don't want to spend 10 minutes drawing while you listen to that. Didn't make a lot of sense there, so I've kind of already annotated a lot of this already. Important points to note are basically everything that I do have highlighted, though. So some major points here are all the points. Point A and point D being the two major ones, right? Because they gave us coordinates there. We have a known bearing along that line, basically AB. We don't have a distance, but we have a bearing. That'll come into play later. And we have some radiuses and departures for these curves. And you'll notice I drew all these out kind of where they fit. One thing to note is these radius points, when they call these out on plans, usually that points towards the center of the curve. So that's kind of how it helped me kind of outline where these are. And I've kind of faked in where these other points along these curves will end up being. And one thing to note is we do have so again, two major points to start with here. We have two coordinates that are given. From that, we should be able to calculate an azimuth and a distance. So that'll probably be step one. And then step two, looks like we can actually traverse along this line here. So they gave us this north 47, 22, 56 east. And then they gave us radiuses and departures, radiuses and deltas, so the angle on those. So with those three, and then we also have this fixed distance that they gave us, we should be able to actually traverse along that line. And that'll help us come up with basically that distance for that red line. And then it'll also give us a bearing once we get down to point C. It should give us that bearing from point C to point D, which is going to be important, because if we calculate that bearing from A to D, and then we have a bearing from A to C, we'll be able to get that angle. And that's going to be really important, because with that angle, we're now going to be able to do law of sines to be able to find angle E. And then we should actually be able to use law of sines to do a whole bunch of other work in here too. So one thing to note is everywhere that we have these intersection points, these are right triangles. Why it's not letting me draw? There we go. Right angle, right angle, right angle, right angle. Got it? Okay. So what does that look like? Step one, find that distance and bearing for AD. So, and we do that by the delta and the latitude versus the delta and the departure. So you'll subtract, on the latitude side, that northing, those two northings, find that the change in the northing, and then you do the same things for the easting, subtract one from the other. To find the distance, you'll have the square root of those two deltas squared plus the other one squared there, and square root of that whole thing. That'll give you that distance AD. And then the azimuth will be cosine to the -1 of the change in the latitude over that distance. And again, those are just our standard departure calculations for coordinates. So with that, takes us to step two. All right, everyone, we're moving on to step two of this calculation. This step two is by far the most difficult piece. Believe it or not, it was most difficult for me. So if it was most difficult for me, I expect it to be the most difficult for you all as well. And that part is fairly simple, right? So we have enough of what they gave us here, of all these radiuses and deltas, to be able to actually do a traverse from point B to point C using assumed coordinates at point B. So I'm going to come over to my table here and show you what is done and where these background formulas actually come from. So we're going to be using the cosine rule and law of sines to be able to do all of this, right? So if you look at this in terms of like what a traverse would actually look like, right? This is kind of how this frames out. We start out with this given bearing at that point B. So we were given that bearing of 47, 22, 56, and we just assume a coordinate value of 0, 0 for B because we don't know it, right? So that's what you'll see what I've got placed right here. We just assumed that, and obviously there's no distance there because it's the origin. So point B becomes the origin, and then we're actually going to traverse using using these different delta angles that we have along here to be able to come up with number one, that final azimuth that comes off. So that azimuth would represent point C to point D. That one's fairly straightforward to go calculate. All we really have to do is add up, starting with that 47, 22, 56, add 15, add 25, and add 20, and that gives you to that 107, 22, 56. So that's the azimuth is the simple part. The difficult part is all the departures. So that's where this does get tricky. If you'll note, I also did reciprocals on all the, or not reciprocals, but factoring in basically that we have 90-degree angles at all of these points, because these are tangents, tangent, theoretically tangent, tangent, and tangent. So all I did was I used, you basically subtract 90 from, in this case, subtract 90 from 47, 22, 56. That gives us that north 47, 32, 4. Then add 15. That gives us 27, 37, 4. Add another 25. That gives us 2, 37, 4. These two are going to be parallel lines because that isn't that 70, 29. Remember, that distance was given to us here on the base problem. As you recall, that 70, 29 there, that's a straight line segment, so there's no angle there. We still need to know the bearing on it so that we can calculate the departures, but there's no angle there. And then as we go along, we'll continue that. The rest of that 20 gets us to that 107.22. So that's where these numbers came from, is by basically doing, subtracting 90 from them. Everybody see that, hopefully? Probably add an east there, shouldn't I? And that is a west and a west. Don't want to confuse anybody with bearings versus azimuths. Okay, so the next part is actually, again, fairly tricky. So we started with that bearing of 47, 22, 56. And then we know that perpendicular line that bisects that arc length is basically half of that 15 degrees, right? So we were given that 15-degree delta. But that C line, coming back over here, and I drew this out so you could see that, we have this angle and we have that distance. That angle relative to that distance, or that perpendicular distance there, is actually only half of that theta angle. Right? Those are the same. So if that theta, if that was theta, that would be theta over 2, and that would be theta over 2, or basically half the angle. So if you look into here, I did this very much on purpose. So we start with that 47, 22, 56, and we add half of that angle. So 15 degrees over 2, which is 7 degrees 30 seconds. So we add that up. That gives us our 54, 52, 56. Then we add the next segment, because, again, if you're looking at this correctly, that angle bisects there. So that is 30 seconds. Oops. 30 minutes. And then this next segment would be the parallel section, would be plus 25 over 2. So that's why I add both of those here. So adding 15 over 2 plus 25 over 2. So that's 7 degrees 30 seconds plus 12 degrees 30 seconds. Which coincidentally just happens to add up to 20 degrees. 74, 52, 56. And then that last segment, because this is that segment of the line that then continues straight. So this is where the other half of that, so this would be that 25 over 2. Has to get added back to that. So that gives us to that 87 degrees, 22 minutes, 56 seconds. And then that last piece gives us that green segment of 97, 22, 56 by adding 20 over 2. And then that final departure coming off of that final angle there, we add that last 10 degrees. So everybody see how I got that? So again, we have like these bisecting or halves of 10 degrees and 10 degrees. Okay? So now that we have the correct bearing or azimuths of those line segments that are perpendicular, again, these are the line segments that are perpendicular to these radiuses, right? So with that, we can now calculate the d distance. So remember, coming back over to our formula here, the L equals that 2 pi times radius times the delta over 360. So that's how we're calculating that L distance. That guy is that guy. So that's how we went ahead and populated that distance table here. Everybody see how that worked? So that's that d times cosine of bearing, or I'm sorry, that L is that 2 pi r times delta over 360. Everybody see how we got that? And those lengths we then plug into the other calculator here to be able to find the little d. Or the other formula for the little d, I should say. Okay? And that first one, remember that first one comes from here. That L is the 2 pi r over delta over 360. And then using that, we now calculate that little d using this law of cosine rule. Okay? So now we have latitudes and departures calculated, and those linear distances there calculated as well. That's how we add and sum all these up to get our overall departure, and then that overall distance. So that overall distance came from square root of the latitude and the departure squared, or the square root of the square of those two. Okay? So now that we have the departure, or sorry, the latitude, and we have that overall distance, now we can actually find the bearing, just like we did earlier in the problem, right? Part one, we found the bearing for that BC using the departures, right? So this is where we use the delta lat over the overall distance. So that 38.586 came from there. The 295.67 came from there. Those both go here. And that's how we get that 82.3005. Okay? So that 82.3005 is that bearing BC. So now why is that super important? So this little triangle here, I just subjugated from actually this drawing here. You can see how I created kind of a larger and a smaller triangle. So triangle within the bigger triangle within the smaller triangle. That's where this one comes from. And now look what we have. Now we have several distances and we have azimuths. And the great thing about distances and having azimuths here is now we can use our law of sines, right? So that's sine A over little a equals sine big E over little e, which is sine big D over little d. So using that, we can calculate those angles. I should add the smaller triangle, we can calculate adding and subtracting this new bearing here that we have. So we calculated that 8230.05. That came from that last step of the problem. And then we have these known bearings that we calculated earlier. And that part is just simple addition, right? So that's that part 3 here. We calculate the angle A, the angle E, and the angle D from the bearings that we had before. And remember, we use the, interior angles of a triangle are sides minus 1 over 360. So in this case, we know the interior angle of a triangle is 180 degrees. So we use those other two calculations. So we had that 4722.56 minus 91.513. That was the new one that we calced. So that gives us an angle of 43.4217. And then angle D is that 107.2256 minus 91.513. That gives us the 16.1743. And then we know the last one is just 180 minus A and minus B, which just so happens to be 120. And that's where that guy came from. Okay, so again, now that we have all those angles, now we can do our law of sines to be able to actually calculate the overall lengths on the big side and the little side of the triangle, right? So big triangle here, this is that distance AE, distance DE, distance CE, and BE. And those correspond to this. This, and that. Okay? So once we have those, then we can actually just use subtraction to be able to find that one. Oops, and it just froze on me. To be able to find that. And that. Okay, so assuming we've gone through this step, right, we found AE, DE, CE, and BE using our law of sines. So we've got that 308, 174, 758, 82, 196, 41, 143, 64. Run through those. Now we're going to use subtraction to find AB and CD. Right, that was that CD is the purple one there. And the other one was that one, right? That AB. So we found those distances. And then now, guess what? Step 5, this is where this gets even easier, right? This is the kind of one of the last steps, right? We want to find those coordinates for point B and coordinates for point C. And we can do that very easily, actually, now. So we have azimuth and we have distance, right, on that segment. So now with that, we can calculate the latitudes and departures from that. And using those latitudes and departures, all we have to do is just add those latitudes and departures to that initial coordinate they gave us for point A. So that initial coordinate for point A was 1999281.5192. and the easting was 6022819.4938. By adding that 11140 to the northing and 12107 to the easting, that's how we get our Bravo, or our point B number. And we do the same thing for coordinate D. Don't ask me why that highlighting kind of moved up on me there. That was weird. Those are the ones we're looking for. Okay. And that is the problem. So that I made that look really easy, but I understand 100% that is not easy. If you actually work this one out, it'll probably take you a good 2 hours to be able to do it, I would guess, if you're doing it all longhand.